Welcome to another lecture in our video lecture series on design of reinforced concrete structures. We are in chapter 3 and we are discussing about the flexural behavior of a reinforced concrete beam. Today we will look at the calculation of design bending moment capacity of a rectangular beam. So in our previous lecture we discussed about the cracking moment, we discussed about the uncracked section of a concrete, and finally we looked at the stress block, and that is the design stress strain curve of concrete. So if I go back to my previous slide here, so first we have the uncracked section here in which both the strains and stresses are linear. Then we have the cracked section here. In this cracked section, the strain in steel bars or strain in reinforcement is less than the yield strain, whereas now the whole tension force in the concrete is taken up by the steel, and the concrete in steel is now ineffective in tension. And finally we have the ultimate state, that is the cracked section at ultimate state, in which the steel strain, that is epsilon s, is now greater than the yield strain in our steel bars, and now the stress curve, that is the compressive stress block, has changed to a non-linear shape. So we will deal with this non-linear compressive stress block, and using that we will derive the design bending moment capacity of a rectangular beam. So let's look here. In this diagram you can first see the strain diagram here, and first I want to discuss about this stress diagram. This is the stress diagram of our rectangular beam for ultimate cracked stage. So here you can see that the stress block or the stress diagram had changed into a non-linear form. And if you remember, when discussing the assumptions of flexural design based on our IS code, there we discussed this parabolic rectangular shape of stress strain curve. We discussed there that the stress strain curve, the design stress strain curve, would be parabolic for up to a strain value of 0.002, and from this strain value to the ultimate strain, that is 0.0035 according to the Indian code, the design curve would be a straight line. So we had a parabolic rectangular shape of stress strain curve for our concrete. This stress block, we call this the compressive stress block or simply stress block. This stress block resembles the shape of this stress strain diagram for concrete. Here you can see the similar shape. For example, up to here we have this parabolic nature, and from this point to this point B we have the straight line. So the nature of this stress block and this stress strain diagram for concrete are the same. So let us suppose that the distance of this stress block, or the distance from this extreme compression fiber to the neutral axis of our beam, is x, and then the compressive stress in our concrete is 0.45 FCK according to our design curve that we looked in our previous lecture. We discussed there how to derive this 0.45 FCK. Now, considering this stress block, we will derive the design bending moment capacity of rectangular beam or rectangular section. And to calculate the design bending moment, we have to satisfy two requirements. That is, there are two principles. The first is the principle of equilibrium, and in equilibrium there are two principles. The first is that the sum of internal forces should be equal to the sum of external forces. So there are no external forces acting on our beam. There are only internal forces, and these internal forces are, one is the tension force and another is the compression force. So we will use this equilibrium principle in which the tensile force in our rectangular section should be equal to the compressive force. And the second principle is the summation of external moments should be equal to the summation of internal moments. So this is the first principle of equilibrium. And the second principle that we will use is the compatibility of strengths. So this principle you can use to determine whether the steel reinforcement in your rectangular sections have yielded or not. Based on these two principles, therefore, we will calculate the design bending moment capacity. And the four major steps that are involved in calculation of this capacity are listed here. First, you have to compute the total tensile strength, and the tensile strength is calculated as the product of area of steel reinforcement AST into the stress in our steel bars, which is FST. So if we assume that our steel bars have just yielded, then the value of FST is given as 0.87 into the yield strength of our reinforcement. So that the total tensile strength is now equal to 0.87 AST into Fy. Now second step is, as the compressive force C and the tensile force T must be equal to maintain the equilibrium of the section. As we discussed in our principle of equilibrium, T equals to C. So you can use this equation to calculate the value of X, that is the depth of neutral axis from the extreme compression fiber. You calculate the value of T and C and equate them to get the value of X, which is the depth of neutral axis. And after calculating the value of X, then you can calculate the lever arm, which is represented by Z. Lever arm means this is the distance between the points of application of tensile force and compressive force. So in this third diagram, if you look here, this is the line of tensile reinforcement as you see in the beam here. So the tension force acts here and the compressive force acts here. So now the distance between these two lines of action, this is the lever arm, which is represented as Z. And D is the effective depth of the beam, which is the distance from the extreme compression fiber to the centroid of this reinforcement group. So use this value of X to get the value of lever arm Z. And finally, you can determine this Mn. Here, N represents the nominal value of moment capacity, or you can say this is the bending moment capacity, which is then determined by multiplying the value of either T or C with the lever arm. T or C, because both T and C are equal, so you can either multiply T into Z or C into Z to calculate the value of Mn. So the four steps I will discuss again. First, calculate the tensile strength. In the second step, equate the value of compressive forces and tensile forces to determine the value of X, which is the depth of neutral axis. Third, calculate lever arm by using the values of effective depth and the values of X. And finally, multiply the value of either tensile force or compressive force with the lever arm calculated in step 3 to get the value of Mn, which is the nominal moment resistance of our beam. Now let's discuss, or let's do what we just discussed in those four steps. First here, what we have done here is we have divided this stress block into two zones. One is this rectangular block and another is this parabolic block. So the compressive force represented by this rectangular block is Cr, and the compressive force represented by this parabolic block is Cp. So now how do you calculate the value of Cr? Cr is given by the area of this rectangle. So area of this rectangle is length, we have 0.45 fck, and breadth is given by the value of 3 by 7x. And finally, this is just the side view. if you look at your 3D diagram, then we have the breadth of our rectangular beam in this section. So this will be our B. And to calculate the volume of this stress block, we have to multiply the area of this rectangular block by the width of our beam, which is represented as B. So we can find the value of B. We have this 0.45 FCK. How do you determine the width of this rectangular block here? What we saw in our stress strain diagram was that this is 0.002 and this stress diagram is 0.0035, and the distance, let's say that this distance is x, is represented by this x here. Using this stress strain diagram, you can calculate the value of this width of this rectangular block, which you now get to be 3 by 7x. So hence the volume of this stress block will be 0.45 FCK. This is the length. 3 by 7x. This is the width, and the width of our rectangular beam is B, hence B. So this value represents the volume of this stress block here. The same thing is written here. CR, this is the compressive force due to the rectangular block, 0.45 FCKB into 3x by 7, which you get to be 0.193 FCKBX. Similarly, the area of this parabolic block is given by 2 by 3 into the same thing here, 0.45 FCK into the width of this parabola, which is 4x by 7 into B. This represents the compressive force due to the parabolic block CP. The same thing we have written here, CP is 0.45 FCKB into 4x by 7 into 2 by 3. The total volume becomes 0.171 FCKB. Now the total compressive force is represented by the summation of CP and CR, which comes out to be 0.36 FCK into BX. So this is the value of total compressive force that is due to this stress block here. Now how do you determine where this total compressive force is acting? Okay, this is our rectangular block. Let me draw it with a different color, and this is our parabolic block. So this total distance is x here, as we have seen. Let us suppose that our total compressive force acts at a distance of xc from this top fiber here. So let us suppose somewhere here. Let me represent the total compressive force as C. Now we know that the resultant compressive force due to this rectangular block, which is CR, will act as a distance of half of this width of rectangular block. So let's suppose that this point CR acts, and this CR acts at a distance of this from the topmost fiber. So the width of this rectangular block is 3 by 7x. So this distance will be now 1 by 2 into 3x by 7. That means the half of this width. Similarly, let us say that the compressive force due to the parabolic block CP acts somewhere here. Now this CP will be at a distance of 5 by 8 times the width of this parabolic block, which is 4x by 7. from this, suppose this is the line of action of the CP. So the total distance of this CP from the topmost fiber will be, this width is 3x by 7, 3x by 7 plus 5 by 8 times of 4x by 7. Now we know the point of application of all these forces CR, CP and C from the topmost fiber. You can equate by taking the moments of all these forces to calculate the value of Xc. For example, let's see here. If C is the total compressive stress, the moment of this compressive stress is obtained by multiplying C with Xc. What we have said here, the distance from the top fiber at which the compressive force acts may be obtained by taking the moment of the forces about the top fiber. So let us suppose that Xc is the distance from the top fiber where the total compressive force acts. So C into Xc should be equal to, first let us look at this, CR into 3x by 14. From here we got 3x by 14 into CR, and CP into x minus 5 by 8 times of 4x by 7. So how did we get this? Let me draw the diagram here again. This total depth is x here, and this distance of only this parabolic block is 4x by 7. And our compressive force CP acts at a distance of 5 by 8 times of this width here, 4x by 7. So this is from this point here. So if you want to calculate this, the distance of this line of action of CP from top fiber, then what you have to do is you have to subtract this value from the total depth, that is x minus 5 by 8 into 4x by 7. This is how you get this whole term here. So now equate this by solve this equation and substitute the value of CP and CR as you obtained from here, CP and CR. Then you will get the value of Xc, which comes out to be 0.416x. So let's see here in this diagram here, this is the point of application of C, and this C is at a distance of 0.416x from the topmost compression fiber, 0.416x. Now finally, the lever arm is given by D minus 0.416x, because this is the total effective depth and we have the point of application of C as 0.416x from top fiber. Hence this is the lever arm. The distance between the lines of application of tensile force and compressive force, and this is given by D minus 0.416x. So before calculating the moment of resistance, let's see here. Now we have determined the stress block distance S. The assumption of the tension steel yielding can be verified by using compatibility of strengths as follows. If you remember, while calculating the tensile forces, we have assumed the stress acting on our steel bars is 0.87 Fy. That means here we have assumed that the steel has yielded. So how to check if the steel has yielded or not? You can use this compatibility of strengths here. Compatibility of strength means you can use similar triangle approach, and then you can suppose that the the strain vary linearly from the neutral depth or the neutral axis. So as per Hooke's law, we have this, the stress in the steel is given by its product of modulus of elasticity and the strain in steel. And this strain in steel can be calculated by this formula here. So how did we get this formula? Let's see here. From this similar triangle, we have one triangle here. The depth of this is given by x, and we have another triangle here whose depth is given by d minus x. So epsilon st is the strain in our steel bars. Epsilon st over d minus x is the depth of this triangle, should be equal to the stress in our extreme compression fiber, which is 0.0035 divided by, this is the value of x. So if you rearrange the terms in this equation, you get the value of epsilon st as 0.0035 into d minus x over x. Now substitute the value of epsilon st and es. The value of es is 2 into 10 to the power 5 Newton per mm square for steel, and the value of epsilon st you get from this equation. If you substitute these two values here, then you get the value of Fs is 700 into d minus x over x. So if the stress in steel Fs calculated by using the above equation, that means this equation, exceeds Fy over 1.15, which is equal to 0.87 Fy, then the assumption of yielding of tension steel is valid, is used to calculate tension force that we did in our previous slides here. So if this value of Fs is greater than 0.87 Fy, then our assumption that the tensile steel reinforcement as yielded is valid here. So this is how you check for validity of tensile steel yielding. Now finally, to calculate the bending moment capacity, so the nominal moment resistance or nominal bending capacity can be calculated by either the multiplication of compressive force and this lever arm or the tensile force into this lever arm. So compressive force we got as 0.36 FCK into Bx, and the value of Z or lever arm we determined as D minus 0.416x. Or if you want to multiply tensile force and lever arm, in that condition there are two sub conditions here. If our steel has yielded, then the value of this tensile force will be equal to 0.87 Fy into AST. But if the tension steel has not yielded, then the value of tensile force will be Fst into AST, where F is the stress on our steel. And the value of the lever arm is the same here, D minus 0.416x. So the second equilibrium equation can be used to determine the moment capacity of the section by equating the internal moment. Mn is the internal moment. That means the capacity of our beam, and externally applied moment is represented as Mu. So how do we calculate Mn? The internal moment capacity may be computed by taking the moment of the internal forces about any point. So this is how you calculate the value of Mn, Cz or Tz. So remember this formula. Now we will talk about balanced, under reinforced and over reinforced beams, but we will discuss this topic probably in our next lecture. We will discuss about balanced, under reinforced and over reinforced section. We will talk about the depth of neutral axis based on whether our section is balanced, under or over reinforced, and then we will look at the limiting values of xu by d based on the type of section that we have. So let's end today's section here. In our next lecture, if possible, we will do a tutorial, or we will complete about this remaining 3 slides. Then we will look at another tutorial in our probably another lecture after our next lecture. So I'll see you soon. Till then, stay safe. Thank you.